Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at converting recurring decimals to fractions. So you might be thinking to yourself, well, what does this have to do with GPs? Well, let's look at what a recurring decimal is. You know, it's something like 0.1 recurring. That just means 0.11111 and they go on forever. So this can actually be written as a GP because this column here, remember that's tenths, hundredths, thousandths. So this is really just 0, the number in front of the decimal point, plus a tenth. That's the first one here. This one is 1/100th. The next one is 1/1000, and you can probably see the pattern here. So if we disregard this number here, the 0, what we're left with is a geometric series. So we have A is 1/10. The reason it's geometric is because there's a common ratio. Each time I'm multiplying by 1/10. So we know that because R is between -1 and 1, 1/10 is clearly more than -1 and less than 1. This, if I go on forever and I keep adding infinitely many terms, it will have a limiting sum. So the sum of this here will be A, which is a tenth, over 1 minus R. So we get 1/10 divided by 9/10. Put that in your calculator. You actually get 1/9. This here is equal to 1/9. So I've taken a recurring decimal and written it as a fraction. So that happens always when you get recurring decimals. The decimal part forms a geometric series in which the common ratio is less than 1 and more than -1, so you can add up all of these terms using the limiting sum formula. So let's look at a few more examples. So let's look at the recurring decimal 0.36 recurring. So this is 0.36, 36, 36, and so on. So this would be the same as 0 plus 3/10 plus 6/100 plus 3/1000, and so on. So this would just go on forever. So the problem is this here, if I just take this isn't of itself a geometric series. See, the common ratio isn't the same. I don't times the same thing by this to get this. Here, I would need to times by 2/10. Here, I need to times by 1/20. But I didn't lie to you on the previous slide. It turns out this is actually just two geometric series together. Let's put all the ones with numerator 3 together. Well, what would that look like? Well, we'd still have our 0, but we'd have 3/10 plus 3/1000. The next term would be 3/100,000, and so on. So that's if I did the 3's. They just go on forever as well. But then I'm going to group the 6's together. So the ones with the 6, I have 6/100 plus 6/10,000. And of course, the next would be 6/1,000,000. And so on. So what I have, this is a geometric series. This is a geometric series. I can calculate their sums independently. Both of these will have a limiting sum because here in this geometric series, I have a common ratio of 1/100. If I times this by 1/100, I get that. If I times this by 1/100, I get that. Similarly here, the common ratio is 1/100. So both of these have limiting sums. Let's calculate them independently. So for this first one here, if I want to calculate S infinity, I'll just call it S infinity 1. That's the ones with the 3's in it. So I just write A over 1 minus r. So I actually get for this 30 over 99, or 10 over 33. So now let's do the same for the GP with the 6's in it. So a over 1 minus r. So here I get 6 over 99, or 2 over 33. So 0.36 recurring is equal to this plus this. It's equal to 10 over 33 plus 2 over 33. So that, of course, just gives me 12 over 33, or 4 over 11. So it was easy to do this without a calculator. So that's what you do when you have different numbers that are recurring. You do them separately, like I did the 3's separately and the 6's separately. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.